So as hard as I was trying to stick to the method of using metric conversions the way the textbook did, I realized just now that I did it the other way in my first class. So, oops, I'm gonna have to apologize to them. So remember, anytime you're switching between metrics, you're gonna use this set of prefixes. Why this is all written on. So we're doing centa, so that's 10 to the negative second, which that's how many of the base unit. So like 10 to the negative second meters per one of the thing that's listed. So per 1 centimeter. I think we have another one in the examples that's kilo, so we can do that one as well. But I inverted it and did 100 centimeters per meter, which in my head, it makes so much more sense. It's just not how your textbook standardizes it. So I'm not sure why I'm apologizing to you guys when it wasn't you, it was the other class. I am making a recording of this. I'll go tell them to watch it. Okay, so when we have units that are squared, so these ones are area. In a second, we're going to do density, which is volume. So like an area is, you're measuring it in boxes. So it's like you have some big space and you're saying how many of my little teeny tiny boxes, those are our centimeter squared boxes or something, are going to fit and fill that space. So that would be measuring area. If you're measuring volume, it's just on a 3-dimensional scale. So you have a container and you want to say how many of my little cubes are going to fit in that container. So when you have that, you use the same metric conversion. So this is the metric conversion that we normally would have memorized. 1 centimeter is equivalent to 10 to the negative second meters. So that's what comes straight off the chart. But if we want to do this in terms of squares, we just square the whole thing. We square the conversion factor. So I put that as parentheses with a squared, but you're going to take that square and turn it to every little part of the conversion factor. So it's like 1 squared, centimeters squared, 10 to the negative second squared, meters squared. So when I say squaring it, that's what I'm doing. Or a simplified way of writing that, because 1 squared is just equal to 1. So 1 centimeter squared, 10 to the negative second squared is equivalent to 10 to the negative fourth. You can punch that in your calculator if you want, or if you remember your rules of exponents, you're going to multiply this times that. If they're being multiplied by each other, then you add the exponents. If they're being raised, then you multiply them. So that's 10 to the negative second squared is 10 to the negative fourth, and then meters squared. Okay? I've also seen people write it as writing it twice. So they would write like 1 centimeter, 10 to the negative second meters, times 1 centimeter, 10 to the negative second meters. That's fine. It'll still give you the right answer, but I think it's a little bit more confusing because you don't already have the centimeter squared unit right in front of your face. You have to like square the units themselves. So I prefer, put the meters squared on bottom because that's what you're trying to get rid of. Put centimeters squared on top because that's what you're trying to get to. And then figure out what the numbers need to be. The way you do that is you say meters and centimeters. That's a metric conversion. So you plug the numbers in, but you have to then square those values if you want the squared version for your conversion. Okay, we'll do another one of these with density, with cubes, to make sure that you feel like comfortable with it. Okay, so what is that? That should be 482 centimeters squared. Did I do that right in my head? Feel free to not do it in your head just to make sure, but yeah. So you should, because negative fourth means you move whatever, I'm not going to explain why. You can do it by just moving the decimal if you want. Okay. I said we were going to do temperature on your own. I'm not going to do any problems with it. That's what I mean, do it on your own, because it's literally just like plugging into a formula. We will rarely use the Celsius Fahrenheit conversion, just because you might use that in lab more often, but we're just not going to see things in Fahrenheit that often. We will work in Celsius and Kelvin, both of those, for lots and lots of problems, and you need to feel comfortable enough with the Celsius measure to have a good sense of like what makes sense. So you should know that water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. It is a beautiful temperature scale because it's so tied to water and easy to remember. It's a little bit ridiculous that we use Fahrenheit that has like no connection really to water at 32 and 212. And you'll also notice that like the degree in Fahrenheit is not the same. Like 1 degree in Fahrenheit is not the same as 1 degree in Celsius, because there's 100 degrees between boiling and freezing, and here there's 180. So like the scales are not even really comparable. You can't say, oh, 212 is similar to 100, so 312 is similar to 200. It doesn't work that way because it's not a linear scale. Celsius and Kelvin, however, are a linear scale. So Kelvin is just offset by 273. So the reason is that absolute 0 in Kelvin basically means that there's no motion. That's not totally correct, but there's no molecular motion. So molecules and atoms are always wiggling around. And at 0 degrees Kelvin, they are as still as they will ever be. And that's why we don't have a negative in Kelvin. So that ends up being 273 below freezing. So that's where we set water's freezing point is 273, and then that's how we convert back and forth. So if you're in Celsius and you need to get to Kelvin, then you just add 273. If you're in Kelvin and you need to get to Celsius, you subtract 273. Okay? The other thing that might be useful to have in your head is like room temperature in Celsius is somewhere between 20 and 25. I feel like 25 Celsius is like 78 Fahrenheit, so that's a pretty warm room. So maybe like 20, 21 is room temperature. That's about 70 degrees. So just kind of having that feel for things is useful. Okay, so the next topic we're going to jump into, and this will help as well to deal with the whole cubing and squaring units, is we're going to talk about density. So I want you to start on this problem. You've got so when it's not a cube, because the dimensions aren't equivalent, isn't that a rectangular prism? Isn't that how you say that shape, or does it have another name for it? Anybody? Okay. I'm going to call it, I'm pretty sure it's a rectangular prism. So it's a cube, but not all the sides are not the same. So it's a rectangular prism with these dimensions. So you can figure out the volume of that prism, and it gives you the mass. So I want you guys to, using this definition, I want you to solve for the density of gold, this little chunk of gold that we're dealing with. So feel free to work with your neighbors, but we're solving for the density of gold given these measurements of this chunk of gold. Thank you. Okay, so volume, if you forgot, length times width times height. So you just take the three sides and multiply them together. So the overall volume, when you're multiplying units, that's how it works as well. You centimeters times centimeters times centimeters is centimeters cubed. That's how we get to these squared or cubed units, is because we're multiplying two different or three different dimensions. And then the density, do mass over volume. Okay, so you should come out with 19.3 grams per centimeters cubed. So there's so many like little life chemistry, whatever, nuggets of knowledge that I'm going to throw at you today that maybe we don't like articulate super clearly in the textbook, but I'm kind of just trying to give you a little bit of intuition. So it was kind of like when we talked about temperature, like it's good for you to have the intuition of what room temperature in Celsius is like. Because I know you guys will know, oh yeah, a room like 70-ish degrees is normal, but you don't know that in Celsius. So getting those kind of feel for things is really beneficial. So another one that's like a little useful piece of information is when we use words a lot of the time to describe mathematical operations. So when we say per, we mean divide. So like if you hear 55 miles per hour, that is 55 miles divided by 1 hour. Okay, those are equivalent statements. To say 55 miles per hour is equivalent to writing it as a conversion factor, really, and writing it over 1 hour. Another one would be like something you're already familiar with, like 60 minutes per hour, right? Those are equivalent things. 60 minutes per 1 hour. Okay, so anytime you hear the word per, it means write it over. And if the 1 is not said, very often it's not said, 60 minutes per hour. We don't say per 1 hour. It's implied. So 55 miles, if you're driving at 55 miles per hour, those are two equivalent things in different units. I can mark how much I've driven in time, or I can mark it in mileage, but they're going to be equivalent if I stay at that speed, right? So anytime you have a unit over another unit, we can turn that into a conversion factor. And density is one of those things. So when we say 19.3 grams per centimeter cubed, it's actually really useful to think of that as a conversion factor and say per over 1 centimeter cubed. Okay, another intuition thing. A centimeter cubed is equivalent to a milliliter. So when they say in medical speak, they say 20 cc's of something, they mean 20 milliliters. And it's so funny to me that they talk like that. I think they still talk like that. I'm pretty sure they do. My sister's a nurse. I feel like I should know that. But because I guarantee that their syringes are not labeled in cc, they're labeled in milliliters. Just like the ones you get, you don't have kids, but when there's liquid medicine, you're pulling that up, it's like in milliliters. So 1 centimeter cubed is not even just equal, it's actually defined as 1 milliliter. So when you have an equals sign, you put 3, that means a definition. So 1 centimeter cubed is defined as 1 milliliter. So what we're saying is that we have a milliliter. Okay, so how do I give you a sense of how small a milliliter is? Again, I'm going back to the kids' medicine thing and being like, well, they take like 15 mils of Tylenol or whatever. So a teaspoon, like a measuring spoon teaspoon, that's 5 milliliters. Okay, so a milliliter is pretty darn small. In water, this is another good one to keep in mind. Water's density is right around 1 gram per centimeter cubed. Again, centimeter cubed is equivalent to milliliter, so 1 gram per 1 milliliter. It changes slightly with temperature. So when you guys do lab stuff, you will like have a table of density of water at different temperatures. But for you, for in here, it's good enough to just kind of have a estimate, a general knowledge that it's around 1 gram per mil, okay? All right, so back to the teaspoon measuring spoon. So we've got a teaspoon, it's full of water. If I were to pour that onto a balance, it would weigh 5 grams. So you can have a sense of how big 5 grams is because it's a teaspoon of water, okay? That's the mass of that water. Gold, on the other hand, if you had a teaspoon worth of gold, would weigh almost 100 grams. Now, how did I do that in my head? A teaspoon is 5 milliliters or 5 centimeters cubed. Those are the same thing. And I was trying to get an idea of how much would that weigh. It's pretty easy. If water is 1 gram per mil, then I know 5 mils is about 5 grams, right? What I did in my head is I took the 5 milliliters and I used the 19.3 as a conversion factor. So I said 19.3 grams per centimeter cubed. And then I multiplied those. Now it's around 100. It's not exactly. It's 96.5. Okay, so I use the density as a conversion factor to figure out the mass of a teaspoon of gold. Okay, it's big difference, right? 96 grams versus 5 grams if it was water. That's because gold is a lot more dense. There's a lot more mass contained in that given volume. So we talked about what density means in actual like practice, what it tells us about the compound that we're talking about, how heavy it is in a given amount of space. We talked about how to calculate it from really basic units. We talked about the fact that the number we get is a unit over another unit, which means we can use it as a conversion factor. And we threw in some like important information. Centimeters cubed is equivalent to a milliliter. Water is about 1 gram per milliliter. So it was a lot of information all in one little slide. So like take a minute to kind of process all of those things, and then we're gonna kind of use some of that stuff as we move along in today's stuff as well as other classes. But the biggest takeaway, the biggest thing that we're going to continue to use today is the idea that if I have a unit over another unit, I can use it as a conversion factor. And maybe I'll do one more example with the miles per hour thing to kind of emphasize this. So let's say that you've set your cruise control at 55 miles an hour. So you're going to have a consistent speed, but you have a trip that you're taking that's 140 miles and you want to know how long it's going to take. Okay. Most people would probably be like, do I divide or do I multiply by 55? I don't know. Let's make sure you know by setting it up as a conversion factor. So you have 140 miles to travel and you want to know how long that's going to take you in hours. Again, your intuition is such that if you tried multiplying and tried dividing, you would know which one was right. In chemistry, you're not going to always have intuition about these things because they are very small little atoms and molecules that you are not familiar with yet, okay? So we need to use this process to make sure you do the problem correctly because you can't just rely on your intuition. So 140 miles, we want to know the hours. So we're going to use this speed that we're driving as a conversion factor. Miles goes on the bottom because that's the thing we're trying to get rid of. Hours goes on the top because that's the thing we want. And then we're going to make sure to keep the number with the correct unit. So 55 miles on the bottom, 1 hour on the top. So that comes out to 2.5 hours that it's going to take for that trip. So like I said, if you had done multiplication, you would have been like, oh, that can't be right because it's not going to be 7,000 hours, 7,700 hours. You would have been like, oh, I'm supposed to divide. But this proves to you why you're dividing. You need to divide by 55 because you need the miles to cancel out and you need to be left with hours. Every time I teach this, I feel a little bit like grateful to my dad, but also like feel bad for people who didn't have fathers that were engineers, because I was on a long car trip with him in the 3rd grade, and I only realized after years later that he was teaching me dimensional analysis, but it was like an example like this, like how many other miles do we have to go to the next rest stop and how fast are we driving? And, you know, he like talked me through the process, and I realize now that he was like teaching me dimensional analysis as a 3rd grader, which is pretty impressive, but obviously I didn't know what it was called until later. Okay. So let's go ahead. We're going to use this and do a practice problem. And these ones are going to be more involved. They're not just, you know, straightforward one conversion factor because we're putting together all of the different pieces. So this is like using density as a conversion factor and doing more complicated conversions. So I will say, in fact, let's do the first one together and the second one on your own. That's a good compromise. So it is a little bit more complicated. How am I knowing that it's complicated? Let's look at the first question. Determine the volume in centimeters cubed of 4.32 kilograms. So when I first read that, I see 4.32 kilograms. That's like my starting spot. And I'm trying to get to centimeters cubed. So when you're reading through a problem like this, don't get caught up in details. Look for the number with a unit. So that's your starting point, 4.32 kilograms, and then look for another unit, centimeters cubed. So I'm starting with 4.32, I'm trying to get to centimeters cubed. Ignore all the other words for now. Then you ask yourself, do I know a conversion factor that gets me from kilograms to centimeters cubed? No, I do not have a single conversion factor that gets me from kilograms to centimeters cubed. In that instance, and I can't remember if we talked about this idea in this class or not, in this instance, when you don't have a single conversion factor, I would recommend using what we call a unit route, which is basically just you're going to plan out your calculation. So I know I'm going to start with the kilograms, and I know I want to eventually get to centimeters cubed. But I know I can't go straight from kilograms to centimeters cubed because I just don't have a conversion factor. As we go throughout the semester, you are going to like assemble a mental, even a physical list of conversion factors. So we've done metric conversions already. We've done English to metric conversions. So this would be like centimeters to inches. And now we're throwing in density as another conversion factor. So if you want to take a minute, like I use a Google, so, you know, like Google stuff. So open a Keep Note and write conversion factors, Metric to metric, English to metric, density. Those are the ones we've done so far. Or a piece of paper. Okay, so I have the density of gold, but I have it in grams and centimeters cubed, not kilograms. Okay, your brain should be churning at this point, saying, okay, well, if I can convert the kilograms to grams, then I could use the conversion factor of density to get me from grams to centimeters cubed. So this is the process I want you going through every time. You figure out what's the number in the unit I'm starting with, what's the unit that I'm trying to get to, and these questions are laid out here, or where are they? Right here. What's the unit of the thing I'm starting with, what's the unit I'm trying to get to, and what conversion factors can I use to get me from one to the other? So I guess we did do unit routes. We use this example here, milliliters to liters, then liters to quarts. So in this one, we're going to go kilograms to grams, and then grams to centimeters cubed. So each arrow represents a conversion factor. And I'm even going to write in a different color what type of conversion factor it is. So like this one is a metric conversion. And this one is density. So rather than trying to figure out how every little problem is different, and then you come to me in 2 weeks and say, like, I just never know which equation to use, start by trying this very stepwise process. Write down the number and the unit that you have. Very often, there's only one number that has a single unit associated with it. You might see the 19.3 and say, well, why shouldn't I start there? The reason why? Because it has a unit over another unit. When you see a unit over another unit, your brain should click and say, that's a conversion factor. That's not my starting place, that's a conversion factor. Okay? The starting place is almost certainly a number that has a unit tied to it, but a single unit. So I start there. I say, what unit am I going to? Centimeters cubed. I say, do I know a conversion factor that gets me from kilograms to centimeters cubed? Once I say no, I don't know that, I better start writing out a unit route so that I don't get confused. So I say, what could I convert to? What conversion factors do I have available? Oh, I have grams to centimeters cubed. Great. How do I get from kilograms to grams? Okay, and then write it out. So then once you're ready with this, we can do the problem now. So I'm not going to put the numbers in yet. I'm just going to put the units in so you guys can see how it's similar to the unit route that I have above. And I am like stretching this to take, like I am taking longer than I will in future things to like really hone in on all the details of these problems, because I would much rather you guys figure this out right now. And like really, if you don't understand a small thing that I did, come ask me like right before we leave from class and say like, I didn't understand how you got this conversion factor, because I would rather you clear it up, or ask right now too. But I would rather you clear it up today than carry it on for 2 more weeks, okay? So, kilograms to grams. The way I do that is these guys match, and I put grams up there. So this point is this first one, okay? So there's gonna be a metric conversion in here. And then the second one, grams to centimeters cubed, the grams goes on the bottom so that it cancels out. The centimeter cubed goes on top. So then this part is that part here. And then I'll be left with centimeters cubed because these will cancel, these will cancel, and all that will be left is centimeters cubed. Okay, so now I just have to put in the numbers and punch it in my calculator. So for the first one, that's a metric conversion. So I go back to my table of multipliers in my head and I say, okay, kilo was 10 to the positive 3. And that multiplier is what we always put with the base unit. So grams is the base unit, no prefix. So 10 to the third grams for every 1 kilogram. Then centimeters cubed and grams, that's my density. So I just need to make sure I take the 19.3 and put it with the grams. So 19.3 goes on the bottom here, and 1 goes with centimeters cubed. And now for the math, just ignore the ones. We don't need those. So 4.32 times 10 to the third divided by 19.3. So stuff on top is multiplied, stuff on bottom is divide. So pull out your calculator and make sure you can do this. Yes, 10 to the third is just 1,000, so you could just type in 1,000, but we're gonna get to stuff like next chapter, maybe next chapter, I think next chapter, that's like 10 to the 23rd. Okay, you cannot type in 23 zeros in your calculator. It probably won't even let you. So you need to make sure you know how to use the exponent keys. Okay, so I will do it up here. Oh, it's there from last class. 4.23, 23 or 32? 32? Okay, thanks. 4.32 times, my 10 to the button is right above log, so I have to use shift, that, third, divided by 19.3. Okay, 223.834. I love this because I'm gonna put 224 and someone's gonna be like, how did you know 224? Why didn't you put 223.8? And that's what we get to talk about at the end of class today, is significant figures. Okay, so I'm gonna put this as 224 so we can answer that question in a second. So 224 centimeters cubed. So what did I just figure out? I figured out a volume. 224 milliliters, centimeters cubed, is about a cup. So I think a cup is 240 mils. So what we're saying is that to make something weigh 4 kilograms, what weighs 4 kilograms? That's about like 10 pounds, I think. 4.32 times 2.2. Yeah, it's 9.5 pounds. So basically a cup of gold, like a measuring cup of gold, would weigh about 10 pounds. That's what we just figured out in this problem. Okay, I'm not gonna do the next one step by step. I'm gonna give you guys 2 minutes to do it and check your answer with what I'm gonna do up here. If you're still confused about it, we can talk about it later. So I will work it up here as you guys are working. I'm going to send the attendance sheet around as well. Yeah. Oh, yep, she had one first. Go ahead.
Yep, all you did was subtract Q. So like, so if I go back here and just insert these 2/3. Yep, so it's just this cube. Yeah, so because we don't actually have a conversion factor, gets you just so you need to
Okay, so you just start with me.
wait, just like this.
Yeah, I was gonna ask the same question, but
So this is a good question. I'm gonna throw it to the whole class. So when you have squared or cubed units, it's almost certainly you don't have that conversion factor. You need to like create it from one that is not squared or cubed. So we don't know anything about inches cubed or centimeters cubed, but we do know inches and centimeters. So we start with that one and then we cube it. So if I take the 2.54 centimeters per inch, and this is one you're given on the exam equation sheet. This is an English to metric, so you're given it, but you do have to go find it. So we know 2.54 centimeters is equivalent to an inch. So the way that we get it to cancel out with this one and so that we can use centimeters cubed is we take that conversion factor and we cube the conversion factor, which means we cube the number, we cube the unit, we cube the number, we cube the unit. So this one is 16.39. I didn't actually do that in my calculation. I just wrote 2.54 cubed, and you can do that too, but I was writing it out so you knew you could do it this way. So 2.54 cubed is 16.39. Centimeters cubed, 1 cubed is 1, inches cubed. So that's me taking the conversion and cubing the conversion so that now the inches cubed will cancel out and the centimeters cubed we can cancel out later on. Does that make sense? It is a little bit weird. Okay, so the end answer, when you plug it in your calculator, what I would do is I would do 1.5 times 2.54 cubed, just because it's easier for me to not have to do it as a separate calculation, times 19.3. Okay, what did that tell me? A little chunk of gold, 1.5 inches on all 3 sides. 1.5 inches, that's smaller than that. That's like this, okay? So 1.5 by 1.5 by 1.5 is going to weigh about 500 grams. Okay? So it's good to kind of remind yourself, like, what did I actually just calculate? Yes, it's good if you got the right answer. I will tell you, you could certainly get a B, maybe a B minus in this class, having no idea what you just calculated, but doing the calculation right. Like if you use this method, you can figure out 90% of the problems without even knowing what the hell you're doing, which I'm not sure if that's a great thing or not, but at least it's like, okay, then the additional 10% of the problem. You probably should understand what you're doing. And like, then there'll be some concept questions, okay? So stick with my method. I will say that density is often taught as an equation. And even I think in your textbook, it'll say density equals mass over volume. I would recommend not going there. You guys have a tendency, and I say you guys, I'm generalizing, but I have noticed that students have a tendency to not do algebra well. So if you were to use this as an equation, D equals M over V, and just try to solve it every time, like solve for mass or volume or whatever, inevitably you mix up, you know, how to solve algebraically for the correct unknown. Okay, so if you do it as a conversion factor, you'll avoid that problem altogether. And you're going to have other conversion factors. You might as well be consistent in the way that you're doing it. Okay, let's talk briefly about significant figures because I want you guys to have an introduction to it. I want you to be able to do a couple practice problems between now and Friday, and then we'll finish up chapter 1 and conversion factors significant figures on Friday. So why did I write down 474 instead of 474.4, which is what the actual number on the calculator came out to be, or 474.4055? Like, why did I decide to cut it off there? Okay. The reason is because when you start a calculation and you're given an initial measurement, in this case it was 1.50 inches cubed, there is a certain precision associated with that. Okay, so they're telling you, I knew that measurement to a particular degree. A good example of this, don't make fun, is that as a chemist, I have translated that into how I bake, and it drives me nuts to measure flour with like a measuring cup and leveling it. So I get out the balance and I say, I know a cup of flour is supposed to be 124 grams. So I'm like, okay, times 2, let's measure out how many grams of flour I should have. It's way more precise because then you don't like crush the flour into the cup. Anyway, so when I say 124 grams, that's because that's how precise my balance is. It does not say 124.000, right? My balance does not go that precise. It's not that good at measuring my flour. So when I say 124, that communicates how good my measuring device was. And if we're going to do a calculation with that, I don't want it to look like my answer is more precise than the thing I started with. So the number in multiplication division, the number of digits in your starting answer generally will match the number of digits you should end with. So in this one, I had 150. I had 3 digits. So I left 3 digits in my answer. That is a very generalized statement, but you'll see in a second what I mean. In the one above, 4.32 kilograms, so I also had 3 digits, so I left my answer as 3 digits, okay? That is true when we're doing multiplication division problems. The issue is that sometimes, particularly with zeros, the digit is there, the 0 might be there, not as part of the number, but as a placeholder. For example, okay, this is 2 slides down. For example, these numbers here, 0.00006, those zeros are just there as a placeholder so that you know the digit 6 is in the, whatever that is, 10,000, okay, that's like 100,000th place. Okay, but the zeros aren't like an indicator of how precise your measurement was. They're just there to tell you where the 6 belongs. Okay, so when I look at a number like this, it might be tempting to say that I have like 7 digits in this number, and so my answer should have 7 digits. Those zeros, we say that they're not significant. They're just placeholders. So one of the biggest challenges with doing significant figures is determining what zeros are significant and which ones are just placeholders. So this is the official rules of how you determine that. And now I'm going to tell you the baby way of telling it, and I get embarrassed every time to do this because it feels so juvenile. But my high school chemistry teacher taught me this, I don't want to say how many years ago, a long time ago, and it has stuck with me and is like literally the easiest way to tell whether a zero is significant or not. Okay, so this is a map of the United States, believe it or not. Okay, this is the Atlantic Ocean, and this is the Pacific Ocean. And we are going to stick a number here. So I'm gonna, I'll use, which one do I want to use? Let's start with the 45. 45.050, okay? If there is a decimal point in the number, we're gonna say that the decimal point is present. So the P is gonna stand for present. So decimal is present. If there is no decimal point, we're gonna say that the decimal is absent. And that's going to determine which side we start on. So in this case, it's present, 45.050. So I'm going to start on this side, and I'm going to go until I hit the first non-zero number, and everything after that is going to be considered a significant figure. Meaning any zeros that I've circled as well are significant. They're not just placeholders. So this number would have 5 significant figures, even though it has those zeros in there. Let me do a couple more examples. So we're going to do 450. I'm going to do that same number, but all in the ones, not point. And then maybe one additional variation. Okay. So these two, the decimal point is absent. So I'm going to start on this side. I'm going to go until I hit the first non-zero number. So I cross through that zero. This one would have 2 significant figures. Same thing over here. Absent, first non-zero number, everything after that. That one would have 4 significant figures. So those zeros I've crossed out, those are not significant. They are placeholders. This one has a decimal point, present. So I'm going to start on this side. First non-zero number, everything after. So that has 1, 2, 3, 4, 5 sig figs. And let me do one more. 0.0045050. Okay? Decimal point is present. I'm going to start on this side. Hopefully you guys can see that. First non-zero number, meaning none of those zeros matter. They are just placeholders. But everything after that does matter. So that has 1, 2, 3, 4, 5 significant figures. And this will work every single time to help you use these rules. So you don't actually have to know these rules. These are an explanation as to why this works. But what it does is help you know which zeros actually are part of the measurement and which are just placeholders to help you know where the number goes. Okay? So we will use this idea on Friday to do calculations to determine how many significant figures should our answer have, knowing what we started with. So try to do a couple of those simple ones in the dynamic study module, or even just verify the ones that are on this list. Hi. Yes.
So when you get the cubes and everything like that, am I able to jump, if I know this, am I able just to jump right to that?
Yep, that's fine.
So I don't have to show this on
Nope,
this.
nope, nope.
Okay.
Yep, that's good. Hey, yes.
So look, on these ones, right? I don't know if I was doing it right when I was converting them.
So show me in your calculator.
Well, I actually did 0.
Okay.
4 to drop it in square.
No, so the squared is just part of this, of the unit. It's not part of the number.
Divided by 10 to the
10 to the negative.
Do you have anything else?
Yep. Yep. Oh, I can already tell the thing for it.
Yeah, I noticed how
Yeah, you could. So you, well, so erase that and then use the second. Yep, there we go. And then -2, or -4, yeah. Yeah, and then N.
We always do that.
Ah! Okay.
As I was confused.
Okay, let me see. Is that -4?
Do you want to do the activity square or do you want to do
Okay, I'm now trying to figure out what did I do. Oh, I know what you did. You didn't use this, you used minus. So when you do the negative, you have to use that. Yeah, which is weird, because I think some calculators let you use the minus as a negative.
Alright, thank you.
That was all. Yep. I'm glad you asked. So that is, you don't have to put that in, because you and I talked about just cubing that number. If you cube that number, it is this number, but you don't have to do that as part of it. As long as you have this, and when you punch it in your calculator, make sure to cube that number, it'll work just fine. Yep. Hi.
Hi.
Were you not on the list?
I was not, but I didn't know if there was like 2 papers or not.
There's not, and we probably need to check why you're not on the list. Whoa.
I was on the list not yesterday, the last time I came
You know
in.
what? It looks like there was, because this ends with a P.
Yeah, I was like,
Yeah,
I just
okay.
wasn't really-
No, you're probably fine. I probably just printed one page is my guess.
Okay.
I'll double check it. I'll let you know if there's an issue, but I think it's fine.
Okay, thank
Yep,
you.
Yep. Hi.
I have a question.
Yes. Okay, so in this one, the reason why it didn't come out right is because this should be cubed, because this is centimeters cubed. So do you have your pencil with you? So if you like put a cube around that whole thing, to get to this one. Okay, so that's where we're planning out the calculation. So it's not so much that you like have the answer or how do you get to it. It's this part here where you kind of planning, where you're planning what you're gonna do. So the question said we had 1.5 inches cubed and we wanted to know what the mass was in grams. So we wrote down this part and this part, and then we said, how can I get from here to there? Well, I don't know, like there's no information that lets me jump directly from this one to that one. The information we did have was the density in grams per centimeter cubed. So that's how I decided I'm gonna have to go from inches cubed to centimeters cubed, and then I can use this one. So it's like you're developing a calculation, or you can even think of it as developing an equation based on, I know where I need to go and I know where I'm starting. And so you have to kind of plan out the steps. So what I would do is maybe go back, let me see if we did some, yeah, we did. So if you look back in our notes from like, not this class, but from the one before, like in this one, like try to apply the same idea and look at this one from your notes and see if that now makes sense. Because we started with milliliters and it wanted us to go to quarts, but there was no conversion for us to get directly from milliliters to quarts. And so we had to think, well, what do I know that can help me get to quarts? And that's where we looked back. So as you're going through the homework ones, as well as looking through the notes again, you need to look for like how to develop that equation. And this whole unit route thing is the best way to do it. Good? Hi.
I gotta go to the activities fair for rugby too.
Okay.
Is that okay? Or
Like
not?
during class?
Yeah, because it's just.
I mean, I'm
My
not like
captain.
gonna take a point off or anything, but I think you shouldn't because I think you're gonna want to be here. I did already, did I do that? I didn't even stop it. I did already record class, so I will post it. So